Hello, everyone. This is Kirsch Mackey, and I am here with the legend himself, Dan Beeker. Hello, Dan.
Hello, hello. Good afternoon. We're here to have fun, and we're going to try to do some analysis of circuit board and hopefully be able to provide some interesting opportunities for people to learn from the two of us. We've got quite a bit of experience, and we'll let Kirsch drive the tools, and I'll be just yammering away in the background. So you vet the schematic to make whatever simple changes that can help improve, if not the behaviors, but at least debugging. And then start thinking in 3 dimensions. Where does the energy come from? How do I get it to where I want to go and keep that dielectric intact? And is it something where I need to have lower impedance, taking advantage of parallel dielectrics? That's where I use either take the same shape and repeat it on another layer, making sure that the dielectrics are the source and the destination dielectrics are well connected in the z-axis, and then look for things that I can put together into that. So I already see challenges with your multiple grounds.
Oh, okay.
I can't help it. My
let me
brain never stops. So
let me fill up the non-isolated
I mean,
the multiple grounds. I
there are
definitely
reasons for mixed domains, absolutely. It just moving from one domain to the other has to be very carefully controlled.
actually let's tackle the this. You said you already see some issues with the multiple ground.
Yeah, I mean, there are reasons to have isolated grounds. I use that for shield grounds. I have those separate. I AC couple the grounds together. High voltage ground and battery management systems, those are often used with an isolated ground. But when you go from, and I see that you've got a transformer, that's how you're doing your coupling. Going from the left side of the transformer to the right side, where you now have or a shield ground, however you want to call that, that those domains can't be crossed over. So you've got, is this an opto isolator? Yeah. So you've got the digital domain on one side, and then your protected domain on the other side. Yep. These types of components are what you use to keep those domains discrete. The challenge is making sure that none of the routing for the left side ever crosses over into the routing on the right side. And
Mm.
those domains, I make the breaks, like if I have ground on two, transformers on one, the left side of the transformer is on layer two would be system ground, the split underneath the body of the transformer, and then the shield ground. And
Mm.
then the capacitor is the same thing across that split in the ground plane onto optical isolator, same thing. It would be across a split between the ground domain, the system domain, and this protected or shield domain. So I
Gotcha.
make, discrete pieces of copper. One side is system ground, the other side is isolated ground. And all of the routing between them is either done through isolation components, capacitors, common mode chokes, opto isolators, transformers, and then nothing ever crosses over that domain at all.
Mm. With that, with awesome. Okay, I definitely want to rush to show you this PCB
Yep.
to see what jumps out immediately.
Is this a 4 or 6 layer board?
This is a four layer,
Okay. 4 layers are very cost effective and a little challenging.
and I'm here thinking after hearing your review, I'm like, man, am I gonna need to? So this is a board I intentionally. Now this is the non-isolated flyback PCB,
I see.
and I intentionally routed things too close or whatever, but all kinds of mess, and
Hmm.
to compare it against something like I call it PCB fixed, but
Hmm.
maybe both PCBs are wrong.
Well,
Okay.
that's where we learn.
And I
Are
know
these
this is
X's
big.
vias, a million vias?
A million views, yes.
Yeah, unless they're needed for thermal, they're just a waste of effort. Because
Mm.
to the fields, that's one giant piece of copper, and it only sees the vias along the edge.
Ah.
It doesn't see anything out here on the bottom. There's nothing happening. And it depends on what you have on layer two. So one's got routing and components. What's on two?
On two is this viewer is gonna show. So if we remove layer top, hide that. Layer two is just a
Solid ground.
all ground.
That's good. So one, two, and three form a triplet, which is the way you start a four-layer board most of the time. So layer three is solid
Ground.
ground.
Yeah.
That means that everything from one to four has to have a ground transition via. And if it's a bunch of power, you need interleaved power and ground vias
Mm.
because you're connecting the dielectric between one and two to the dielectric between three and four. And to get there, you've got to have two conductors, power and ground, signal and ground. I would never put ground next to ground on a board because I've wasted a dielectric layer.
Mm.
The between three and two, nothing is happening. It's just there. So if I'm paying for the dielectric, I would like to use it for something. So I do all that I can on one and three.
Mm.
And then if I want to do a lot of things, I would use either ground on four or ground flood on three to create dielectrics between three and four that I can use. But when I go from one or three to four, I need a ground transition via
Mm.
to get to that space. And where I don't have adjacent planar copper, like on three, that's reference to or next to the signals that I'm routing on four, then I need to make sure that there's coplanar ground flood on four so that at least there's the dielectric between the ground copper and the signal trace on that layer. But ideally, I would want to have as much as possible so that I'm using the width of the trace instead of the edge of the foil to create my transmission line.
Meaning.
So everywhere you go from four to one, you need at least a single ground transition via where your heavy power is, you're going to want multiple power ground vias.
So, for since I'm taking this, so what I have on ground on layer four is more ground. And then layer four has this V out that
Mhm.
goes here, which I guess this is okay.
In
This
order
over
to
here,
get, because it's going to, the connector is coming out of the top, right?
yes.
So the energy is going to come from the dielectric between three and four
Uh-huh.
and between the two pins of J3 and J4. So between those, that needs to be clear. And where you've got this V out trace routed across here to the left,
Mm-hmm.
it needs ground transition vias. So how much energy are we talking about? The switching, the IC's on the top, right?
The IC's on the
Switching
top.
regular. Yeah, so if this is the output from the IC that you're driving across, you're going to need to get to four, you're going to want more than one ground via and
Mm.
interleave power and ground vias. Like so if you look at the new high performance SOCs, their core supplies are a grid of interleave power grounds. And that's so
Mm.
that they can deliver energy to the substrate, to the die, with as many parallel dielectrics as possible. So
Uh,
every discrete pair of power and ground, power one, ground one, power two, ground one. That's a discrete dielectric. Each one of them gives you a separate place for the energy to flow. So
mm.
multiple power grounds give you a low impedance Z axis And then you'd want to have this trace routed wide enough that your impedance of that transmission line is going to be low enough to deliver your current from the output of the regulator to the connector pins.
Hmm. With
Because you're
these
trying to take that energy and charge this capacitor over here.
where's
You know,
my
I would
3D view?
I would want to maybe have at this switching speeds, it doesn't matter where the capacitors are because this transistor is switching really slow. So
So I
you're well within the 20th wavelength, I would suggest at this time, which is what
got
you
you.
want to have stuff. So that, and then just make sure underneath your discrete components, you never flood underneath them. They need to see the
Never.
dielectric in the adjacent space. So a capacitor or inductor, resistor, diode, connector, anything on layer one needs to see the energy that's between one and two and in that dielectric. So you can't flood underneath discretes. And then, but they do need ground on two because that's the second half of the transmission line.
When you say cannot flood underneath discretes, you said the reasons because they need to see
Their job
the
is to work on the field that's in the dielectric. And
Mhm,
if I have routing or flooding underneath a ground, a transistor, a resistor, or a diode,
mhm,
it obstructs the view of the field that needs to see the body of the transistor, of the diode or the resistor. And it has to find its way from the space between one and two to get to the top of the flood on one and find its way back over underneath the body of that discrete component, get into that component, and then get to the other side and then find its way back around and back again. So it increases the impedance of that interface, takes longer, more wave cycles. So the better that that component can see the energy that its job is to work on, the more efficiently it can do its job. You know, resistors need to see the field there. They need to be able to convert a fixed amount of electromagnetic field energy into kinetic energy. That's what their job is, to eat field, turn it into heat. Capacitor's job is to catch field and store it. So that there needs to be a direct connection. A capacitor is like a vertical dielectric connected to your board.
mhm.
So the energy comes along in the space between one and two, and then goes into the space between the two leads of the capacitor. And then same thing when it needs to source energy, it comes from between those two leads into this horizontal dielectric. And if you put anything in there to obstruct the delivery of the field, it takes more wave cycles. Maybe the time it takes for each wave cycle, because it has to travel longer, is more. And then all these waves, every wave front is a source of evil, because that's where all crosstalk occurs, radiate emissions, everything happens at the wavefront, because that changing E field is what creates the changing H field in the conductors, which then cause a changing E field in the next space, which now causes a changing H field in the next conductor, and it walks its way through until it gets to a space that's large enough that it doesn't find another conductor, it finds the air around it and
Mm.
radiates into space. So those are things that happen. Again, it's about dielectric awareness, knowing what dielectric the energy starts in, where I want it to go, and how do I make sure that in all three dimensions it is always completely intact.
So it's gonna like walk around if I put flooded the ground
It's
underneath the
always
components,
crosstalk.
it's gonna
The and the beauty of ground flooding is that it presents a larger piece of copper,
uh-huh.
and you have a fixed amount of a changing E field of a
Mm,
fixed amount. It's only going to create a certain amount of H field.
mm,
Well, a certain amount of flux. That flux can either be concentrated in a small piece of copper, or it can be distributed across a larger surface. So as a signal goes between a trace and the ground plane, as it's switching, you're going to create a magnetic field related to that wavefront on the trace
mm.
with a fixed amount of flux. it's doing the same thing to the plane, but it's the same total flux. So because it's not going around a 10 mil trace, it's 10 microns thick,
Mhm.
it's going around 4 inches of copper. So, but it's the same total energy. So the flux density per cubic centimeter is significantly lower, and you get this shielding effect. Ralph says it's about 200 dB between the top and the bottom of a plane, but it's because that changing magnetic field, again, it's a fixed amount of flux related to the wavefront, is distributed across a much larger surface area. So adding ground flood between signal traces is better than an open space because it has to do another leapfrog, and that flux density is distributed across a larger surface area. So
But
that the
putting
resulting changing magnetic field has a lower total energy and also a lower frequency. The wavefront gets collapsed. All kinds of good things happen. Ground is your
awesome,
friend.
but putting it underneath the components in this
On the
circuit
next layer
on the next layer
is good, but
is good.
underneath the component, because it has to find its way to the top of that copper.
Oh, so you're saying don't put
If
ground underneath the component on layer one.
on the layer one, yeah, on
Oh,
layer
okay,
two
okay,
is good.
okay.
Now, people talk about if you do leave flood underneath a resistor or a capacitor, for some reason, you need to put ground vias at each end of the part underneath the capacitor, or not the capacitor, the resistor or the inductor,
Mm,
so that the field goes between one and two up the side of the vias to the top of the flood on one and the body of the inductor, and then back down into the space between one and two.
mm,
Then you're giving it a clear path to go to. Otherwise, it will have to go find the nearest ground via. So go all the way, it'll go along one, along two, find a via, go to the flood, the bottom of the flood on one, find its way around to the top of one, and make its way finally over to the inductor or the resistor or diode that you're trying to deliver the energy to. So that convoluted path is what causes problems.
mhm.
Again, reducing the travel time, reducing the space, giving the energy a place to go that it has no choice, that you have chosen yourself. That's part of the design. Plumbing. It's just three-dimensional leaky, I call it leaky water pipes.
Ah, yeah.
Three-dimensional plumbing. And if you have to be dielectric aware, and the results are good decisions in how you do your placement and routing. And the results are better efficiency, lower power consumption, better immunity, better radiated emissions. Overall system performance is improved just by managing simple things like ground floods and ground vias. And then in this case, if you had the isolated grounds, you would have on layer two and three in this case, on one side of the transformer and the capacitors and the optical switch, you would have the system ground, and on the other side of the split, which is marked by these components, would be your shielded ground or your special ground. And I
Mm.
do that for Ethernet, for USB, anything where I have a discrete shielded ground or high voltage ground. The movement of energy between the two domains has to be done, very well controlled using these types of components, common mode chokes, transformers, opto-isolators, capacitors for AC coupling.
And you route those split up those two separate grounds to their two separate
Then they do everything on these sides, and then these components are bridging the gap.
mhm. And so the ground on the right would go to like a different like
Yeah, whatever your domain is, if that was a
domain.
shield or enclosure, whatever that needed to be. And then
Mhm.
you would make sure that you didn't route anything across that split, because once you do that, then you violated the whole purpose of having the isolation. I've seen a lot of times where people have especially the filter elements for Ethernet.
Mm.
And they'll have the schematic be drawn so that these components are connected to system ground.
Yeah, I've seen
That
that
just
before.
violated the whole purpose of the common mode choke. Those are designed to take care of energies that are coming from the outside world. They need to catch those, release them, and deal with them in that domain, and not allow that energy to make the crossover into the protected system domain.
Mm.
So it's all, what dielectric am I in? How can I cleanly deliver that energy to the next dielectric? You know, if if there is indeed a separate ground conductor being used, that pathway has to be in only one place. That's why a lot of times people use inductors and ferrites and other stuff to create isolated grounds. Well, that's fine as long as everything that you use is only reference to that ground. So if you're trying to do a
Mm.
special A to D ground that's isolated through an inductor or a ferrite, and you bring sensors in that are not powered by something that's reference to that special ground, you bring these signals in, they have to go find this connection and make their way back in. So you've created this huge discontinuity in the flow of energy. And there's always more than one. All those signals now share the same space. You encourage crosstalk, you reduce the accuracy of your reading just by trying to make a special ground. And there's so many, and people did that in the old days. That came out of not understanding how things work. And we were using geometries that were so huge that doing stupid things didn't break them, but doing stupid things weren't the right things to do. And unfortunately, most of the design guidelines have fallen out of what didn't break it rather than the right thing to do. And our mission, and you and I agree on this, is to try to help people understand what are the right things to
Mm.
do. How do you really manage these energies properly? And it's designing the space. Again, that's why I'm always saying it's all about the space. So with that, I think you've got a lot to think about. Hopefully our audience is going to have a lot to think about. And we'll be watching for questions. I think there will be a good way for us to start some interaction with the rest of the world. So thank you for the opportunity.
Absolutely. Thank you so much, Dan. Okay, you heard from the legend himself, and we checked out these designs. Let us know your questions and thoughts and opinions. And until next time, we'll see you in the next video. Peace.